now we have Matt Trodden talking about particle physics and Cosmology 2.
Well, thanks. To use this nice phrase that Ed just used, I'll try to deliver a wonderful siren call for the observational cosmology and do for fundamental physics, or vice versa in this case. As I said in my first talk, I talked about the baryon asymmetry, and it was a placeholder really to describe a lot of the different techniques that come into trying to calculate the quantities we need to connect fundamental physics, particle physics with cosmology, and it allowed me to talk about phase transitions, the beautiful non-material structure, gauge theories themselves, and things like that. In this talk, I'm going to talk about dark matter. I'm going to have less equations than last time in this talk, and that is so that you can have a rest before I present you with lots of equations in tomorrow's talk. So as I gave you yesterday, there's this sort of description of what I'm trying to cover in these lectures. Today I'll stick to dark matter mostly, and my purpose today will be, as yesterday, to try to make a general point, but then to focus on a specific class of models so that I can make a fairly detailed argument, although I won't necessarily present all the equations to go with it. And then tomorrow I'm going to sort of change tack slightly, and I'm going to give a talk that should in some ways complement the nice talks you've heard from Ed. I'll be motivated tomorrow in tomorrow's talk about attempts to modify gravity as an attempt to understand the accelerated expansion of the universe. I won't talk about sort of phenomenological approaches in 4 dimension. I'll instead expand on some of the things I'll say today about extra dimension and discuss how people have been trying to use those models to get accelerated expansion out and an interesting class of 4-dimensional field theories that arise as a result. And there should be some connections to many of the things I say today as well. Okay, so I'm going to start, since this is partly a school course, I'm going to start by telling you things that many people will know, but by laying them out quite carefully. I'm going to give a brief basic thermal history of the universe discussion, in particular the discussion of why it is that in an expanding universe, particles can freeze out and how their abundances can be set by their interaction rates and the temperature of the universe. I'm then going to talk about WIMP dark matter, and in particular why it is that when we think about WIMP dark matter, the weak scale, the W is for, naturally emerges. And this part of the discussion will be purely about cosmology with a hypothetical set of particles that have a hypothetical set of interactions with some cross-section. Then I'll switch hats and I'll start to look at things from the particle physics perspective. I'll cease to talk about cosmology for a moment, and I'll go back to my discussion of the Electroweak model from yesterday. And what I'll do there is try to convince you that within the context of the Electroweak theory, an extremely well-tested theory of particle physics, of course, that the weak scale is very, very special. Okay? It's special because, of course, that's where we hope to find the Higgs, and I'll talk a little bit about why that is. But it's also special because of something called the hierarchy problem. And I'll describe that briefly, and it will have some connections to what I'll talk about tomorrow also when I get to talk about the cosmological constant problem. So this problem of particle physics has a number of solutions. I'll speak in a little bit of detail about 2 of them, supersymmetry and extra dimensions, to describe why it is, how it is that those models work, and why it is that they solve these problems of particle physics. And again, I'll just try to make a point that I made yesterday. This has nothing to do with cosmology at all. This is to do with the very well-posed particle physics problem, to which there are a number, and I'll just describe 2, of very well understood particle physics solutions. But then I'll try to make the point that these examples, and in fact a much wider class of examples that you could think of to solve this problem, will naturally give you a class of particles that will provide you with the properties that emerge from our cosmological discussion up here, WIMPs. This connection didn't have to be there at all. And so while I will comment on other good particle physics candidates and direct you to other people in the room and indeed a poster where you can find some discussion of them, I'm going to stick with this. I'll give you a very optimistic example at the end of how particle physics and cosmology together could try to come together and identify what dark matter is in coming years. So I'll stick to these WIMPs there, and then I'll summarize. Okay, so let's do some very elementary cosmology to start with. So, I should just comment, I just wanted to say that, the point of this thermal history is, of course, that as you go up in temperature and energy, you're going back in the history of the universe. Yesterday, I talked about cryogenesis and its possible connection to grand unified theories and its connection to the weak scale. Today, I want to talk about temperatures around here, the WIMP decoupling scale around the weak scale of GeV. Okay, so let's do some very simple thermal history. If you have a species of particles in the universe, then if their interaction rate is larger than the expansion rate of the universe, then very loosely speaking, when these particles decay, then there's enough time and enough energy around for the products of that decay to get back together, recombine, and form particles. There's an equilibrium that can be established in the universe. And that's an interesting state for the universe to begin, but it's not one that is likely to give any particularly interesting long-lasting physics at late times. However, if the interaction rates of particles in the universe fall below the expansion rate, then it's possible for particles to freeze up or decouple. So if the rate of interactions is much less than the expansion rate, then, again, roughly speaking, for example, particles can decay, the expansion rate of the universe is fast enough that the products cannot get back together again, and so you're in an out of equilibrium situation. So when does this happen? Well, usually you have equilibrium in the early universe. That's just generally true. The interaction rate is typically given by the number density of particles times the thermally averaged cross-section times the velocity of particles. And that velocity can get very large in the universe, of course. So here's the description of what's going on. But as we'll see in a moment, as the universe evolves, the density of particles lowers because the universe is expanding. And it gets so low that equilibrium could be no longer maintained. And in fact, in the current universe, the temperature is so low that really no species are in equilibrium with the background thermal particles in the universe, which is the microwave background photons. Everything has fallen out of equilibrium. So how do we describe particles in equilibrium? If you have weakly interacting particles, in which it makes sense for me to write down some interacting theory that I understand, then of course you describe them with a distribution function. So here's that distribution function, with a plus for fermions and minus for bosons. And the energy density here, the energy I should say, of these particles is described by this dispersion relation here that relates the energy to the momentum of particles and their mass. And if you have this, of course, then, as you learn in your first cosmology class, or in fact in your first statistical physics class, you can describe the number density of particles via this integral, where g here is the number of degrees of freedom. G will appear in a number of places in the equations I use here. I'm not going to attempt to describe the different g's that come along. Just trust me, they're taking account of different species and spins and other such things that are just details. So you have a number density. You compute the energy density via the distribution function by sticking the energy in there, and you can compute the pressure. So if I give you a set of particles that are in equilibrium, I have all the information I need to compute many of the things that are important for cosmology. So that's nice. Now, these integrals I wrote down are actually very easy to perform in two limits that you know. The first one is the relativistic limit. If the temperature of the universe is much larger than the typical mass of particles, then in that energy description, energy equation I wrote down, the momentum dominates that system. These particles are relativistic, and then you can compute these quantities here. Number densities go like T cubed, energy densities go like T to the fourth, pressures go like this. It's radiation. They're relativistic. And in the other limit, you could do it non-relativistically, and you get sort of a Boltzmann suppression here. These things are cold, they're non-relativistic, so their energy density is just given by their mass and the number density. And the pressure is given by this, which is much, much less than the energy density. And of course, these things are essentially dust. In other words, the pressure is essentially zero, at least at the level of where you're considering the equation of state of these systems. Now, if the species that you're interested in freezes out, i.e. its interaction rates become less than the expansion of the universe, while it is still relativistic, then the number density of particles just goes like t cubed at the free zone. That's it. And then after that point, these particles, since they're relativistic, just redshift away the way photons do. They become sort of unimportant quickly. In fact, what they really do is remain comparable to the photon number density today. The number of whatever particle you're interested in today has to be something like the photon number density today, because this is just photons behave, and that's some very small number, and we know that radiation is an extremely subdominant component of the universe today. So these particles, while in principle interesting to our understanding of the universe, are not going to be around in great abundance today. This is the way they're produced. Now, there's an alternative, of course, which is that particles freeze off when they're non-relativistic. It's much harder to compute the abundance, I should tell you, when this happens. And what you have to do is integrate the Boltzmann equation. So here's the Boltzmann equation. It describes in a little more detail what I said in words on the last slide. The number density of particles depends on the dilution from the expansion of the universe and the annihilations that are happening between particles. It's a competition between these two rates that allows you to make this statement about freeze-up that I made on the last slide. But if the particles are going to freeze up when they're non-relativistic, it's, then as I said, it's much harder to compute this. So here I'll just provide you with an approximate answer that's going to be good enough for the level of detail I'm going to cover in this lecture. Namely, the number density of a particle species for temperatures less than the freeze-out temperature, if they freeze out when they're non-relativistic, is related to the number density of photons in the following way. It's 1 over the mass of the particle, 1 over the Planck mass, and what appears in here is this annihilation cross-section, which is computed at the temperature, when the temperature is equal to the mass. And it's a convenient way to normalize this expression. And since the non-relativistic number density, if you have a particle species that freezes out when it's non-relativistic, is just given by the mass times the number density, because all the contributions from the pressure, etc., are irrelevant, then it's quite easy to compute the contribution to the critical density that a species like this will make. And it's given by this expression here. It's the number density of photons divided by combinations of the Hubble constant today, Planck mass cubed, and this cross-section that I mentioned here. Excuse me one moment. Now, this calculation is completely cosmology, and I've just got this hypothetical species X. Okay? I can put numbers into this expression, and if I do so, I get this. So it's 1 over cross-section computed at the temperature of the mass times 10 to the 9 GeV squared. Units of cross-section are 1 over mass squared in my definition. So this is dimensions that you need. So just to summarize, initially in the universe, the interactions dominate. Eventually, particles reach their equilibrium number density. They start to follow, this is co-moving number density. They start to follow this Boltzmann curve. They're getting heavily diluted. But at some point, before they can get completely diluted by the Boltzmann term, the dilution effect of the expansion of the universe starts to WIMP, stops them from being able to find each other and annihilate, and they freeze out at some co-moving number density. And that's then fixed. And they just dilute away with the expansion. Now, a particularly interesting possibility from what I wrote down on the previous slide is that if the particles in question are weakly interacting I mean interact with a strength of order the weak interactions in the particle physics sense, not just not very strong in the weak sense, then sigma 0, this whole thing I wrote down on the previous slide, takes this form. It's given by approximately alpha weak G Fermi, where G Fermi, the Fermi constant, is about 300 GeV inverse. This is just a constant of nature, comes out of the weak interactions. And alpha weak also is the weak coupling constant, the dimensionless measure of weak coupling. It's about 1 over 100. You plug the numbers into here, what do you find? You find out that sigma 0 is about 10 to the -9 GeV inverse 2. And if you recall what I wrote down 2 slides back, then that expression I wrote down there yields omega x is about 1. I hope I don't need to emphasize that I'm omitting terms here of order 0.1, 0.3, 10, You know, so anyway. But the point you should take away from this is the following. That, quite remarkably, so far it's not particularly remarkable, so far it's just a number. If I have weakly interacting particles, then the abundance you should get, they will freeze out when non-relativistic. They will scale away, they will have low pressure because they're non-relativistic, they'll be cold. They will scale away with the expansion of the universe, and their contribution to the overall energy budget of the universe today will be of order 1 or a 10. It won't be a millionth or something like that. Now, so the point is that if dark matter is flowing through the freeze-out non-relativistic particles, then in fact what you would expect is that you need an annihilation cross-section at the weak scale. Now, this was just cosmology. I mean, I don't mean just cosmology, I don't insult anyone, but it was only cosmology so far. If you were in the business of inventing models for dark matter, then what you would immediately run away and do, not that particle physicists would ever do something like this, is really start writing down appropriate Lagrangians at the weak scale. Willy-nilly. They would just run away and start writing down Lagrangians that gave you the dark matter you wanted. That's not what you really want to do, of course. As I tried to emphasize yesterday, the power of this interaction between particle physics and cosmology is the fact that there should be multiple arguments for the kind of models that you're interested in, coming from particle physics and coming from cosmology. It's the fact that these things complement one another, which makes this such an interesting subject. So of course, the story is much more compelling than just realizing that the scale is important and running away and writing down models. Okay, now let's switch hats slightly and go to particle physics. You'll recall from my last lecture on Tuesday that the Electroweak theory that we're currently testing in colliders, is this spontaneously broken quantum field theory with the SU2 crushing 1 gauge groups. There's strong interactions in there too, and I will talk about them today, just as I didn't really talk about them last time. They're very interesting, they're just more complicated, to say it mildly. So you've got this Lagrangian. I'll just remind you that it's got some U1 gauge fields, it's got some SU2 gauge field, and crucially, it has this thing called the Higgs field involved. There are fermions too. So if you care about the equations from last time, they're there just to remind you. It's easy enough to repeat my slide. But the point I want to make here concerns the Higgs field. The Higgs field is a thing that breaks the symmetry. It takes an expectation value at 0 temperature, and today, that's really all I'll care about. Okay? So I won't be interested in the nature of the phase transition today. It takes an expectation value because it has a minimum of the potential away from 0, and that is an explanation for the masses of the elementary particles. So let's focus on the Higgs. The Higgs field breaks the symmetry, gives mass to the gauge fields and the elementary fermions, such as the electrons. People like to say that the Higgs field is the origin of all mass, and this is, of course, not true. If you were to pick up a proton, you would find that the Higgs is an irrelevant part of its mass. Most of its mass comes from all the messy, strong quantum chromodynamic interactions that are going on. But for the elementary particles, such as the electron, indeed, their mass comes from the Higgs. Now, the mass of the Higgs itself is, of course, a very hot topic. We have devoted huge amounts of energy and dug very long holes to try to figure out what it is. It's not precisely fixed, but it's given by this expression, where V is the expectation value in that last slide, is 246 GeV. So the mass of the Higgs comes down to what its coupling is. Now, we haven't discovered what its mass is, but the Electroweak theory is an extremely precisely tested theory. Whenever you write down an expression in the Electroweak theory and go to a collider and marvel at the fact that it agrees so well with experiment, what you're doing is taking into account all the possible quantum corrections that you can imagine that take part in the standard model. And the Higgs should contribute to those quantum corrections. It should appear in loops. And because of that, even though we have not found the Higgs particle, if the Higgs particle exists, its very existence through virtual effects should manifest itself in the measurements of observables in the Electroweak theory. And there are many of those, and they're exquisitely tested. And so in fact, you can put together a combined fit on what you think the Higgs mass should be. So this is kind of what I mentioned yesterday in graphical form. This is delta chi-squared. If you want to know what delta chi-squared is, you should just ask the Chia. She's over here, she'll tell you. But in any case, what you're really seeing here is a plot of what the allowed Higgs mass is and what the excluded ranges are from experiments. Down here is completely excluded and has been for a long time from the left experiments. So below about 114 GeV. This is what I talked about yesterday on Tuesday when I was talking about where the Higgs mass could not be lower than. This band here is slightly old. I think this band is a little wider. It's a slightly older plot than the completely current one, is where the tevatron has managed to exclude the Higgs at a higher mass. And you'll recall that I mentioned yesterday that at least on the face of it, it seems like you should be able to exclude lower masses more easily, but the decay rates are different. Just getting channels are different up here, and the backgrounds are lower. You'll notice that the delta chi-squared is becoming big very rapidly the further away you get from this low mass region. And in fact, what this graph is telling you is that precision electroweak measurements, having not found the Higgs at all, are already telling you it should be really light. In fact, what they're telling you is it should be lighter than we've already excluded, but it better be down here in light. If it's up here, then it's really not what you expect from precision electroweak fields. So that's quite remarkable. It tells you that the Higgs needs to be light. 100 GeV, 120 GeV, around there. So what's the problem? Well, the problem is that the Higgs is a scalar particle. All particles in the standard model pick up quantum corrections to their masses, to their interactions, etc., etc. But many of those corrections that they pick up are logarithmic. The higher the scale is that you look at it, the logarithmic change in things like the mass. But scalars are different. Higgs is the only scalar we think we absolutely categorically need, unless you're a cosmologist, in which case you need about 50 to make inflation calculation. So if you compute quantum corrections to the Higgs mass, then what happens is, because it's a scalar, they are quadratically divergent. And tomorrow when I talk about the cosmological constant problem, I'll flesh this out in a little more detail with maybe an integral reward or something. But here's what happens to Higgs. You take the Higgs, and you have to compute contributions to it from virtual loops. And here I've just drawn the top loop because that's a big one, because the top's Yukawa coupling is large. And when you compute these loops in a quantum field theory, you have to put a cutoff, because of course the electroweak theory isn't the true theory all the way up to the quantum gravity era. So you have to cut it off wherever your new physics appears. So either there's new physics at some scale above the electroweak scale that we don't know, we'll talk about that in a minute, or at worst, it's got to appear at the Planck scale, because the electroweak theory is not a quantum theory of gravity. So if I do that, I put the Planck scale in, then the Higgs mass that you measure consists of the Higgs mass that you write down when you write down that electroweak Lagrangian, plus quantum corrections that are of order the cutoff that appears in these loops. And if that's going to be the Planck scale, then I need to introduce a Planck scale object here. By the way, there can be a minus sign here, so don't worry about the signs. And if I want this observed Higgs mass to be light, as the last slide tells you I do, these numbers have to cancel one another to about 1 part in 10 to 15. And that's an extreme fine change. This is what particle physics is called technical naturalness. It's not that there's a small number in your theory and you don't like small numbers. That's naturalness. Technical naturalness is there's a small number in your theory and quantum effects conspire to make that an enormous number unless you do some extremely careful fine-tuning at this kind of level. This is what's called the hierarchy problem. Because it's the difference between, say, the Planck scale and the weak scale. And it's a huge problem. There's another way to phrase this, since it's the difference between the Planck scale and the weak scale. You can just say, why is it that gravity is so much weaker than the other forces? So one way to parameterize this difference between what's going on is to take the Newton constant that describes gravity, given by 10 minus 3, 33 GeV minus 2, and compare it with this thing I talked about earlier, the Fermi constant. So the problem with the hierarchy problem is how can you explain the disparity between these two scales in a sensible way, and thereby avoid the conundrum that quantum mechanical corrections to the standard model place you in. Now, one framework to do this is to say, well, we love gravity. Gravity is fundamental. The Planck scale is the fundamental scale of all physics. The weak scale is very unnaturally small compared to it. In other words, the electroweak forces are naturally strong. And to try to come up with a model that explains why this is unnaturally strong. An example that does that is SUSY, and I'll explain that in a moment. You could take a completely different point of view. You could say, I don't like gravity that much. The weak scale is the fundamental scale of all physics. But the problem here is not that the electroweak force is unnaturally strong, it's that gravity is ridiculously weak. And if you want to tackle things this way, there are ways to do it using extra dimensions. And I'll describe those in a little bit of detail soon. There are other ways to do this too, as I'll mention, but these are the two that I'm going to focus on today. So let's move to supersymmetry. Supersymmetry really is a radical new idea. Everything that we've talked about in this conference so far has involved gravity, which deals with general covariance, that set of symmetries, or particle physics, internal symmetries, gauge symmetries. Supersymmetry mixes these things up in a way. It's a space-time symmetry that acts on particles. Okay? It mixes, in particular, bosons and fermions. And that's a very strange thing. It relates bosons to fermions. And it has a huge number of consequences. But the one thing I want to focus on here is that if SUSY is exact, well, let me step back. If you have a supersymmetric theory at all, then your particles multiply because every particle has an associated superpartner. Because as I said, there's a mixture between bosons and fermions. So an electron has a partner, a photon has a partner, etc. And when you compute, if SUSY is an exact symmetry, so we could have a conversation about this, which is to do with the level of symmetries and operators acting on states, but I don't think we need to. If SUSY is an exact symmetry, then the particles and their superpartners appear in pairs when you compute quantum loops. So in particular, this horrible loop that I wrote down for the Higgs mass earlier in the SUSY theory becomes this. There's the thing I originally wrote down, and there's another loop that comes around that carries with it, instead of the top, carries with it the partner of the top. In this case, the stop in the nomenclature of supersymmetry, super top, superpartner of top. So that's fine. Why do I care? And I care because supersymmetry is very special, and if SUSY is exact, please cancel. So if SUSY is exact, all this fuss I made on the last couple of slides about quadratic divergences goes away. And I don't have to worry about the effect of these loops. Things don't run off up to the Planck scale. There's no hierarchy problem. It's very good. In fact, there are no quantum corrections at all if SUSY is exact. At least that I care about this way. So that's pretty nice, actually. We, unfortunately, live in the real world, although after a few days in Puerto Vallarta, it's not that bad at all. This is not quite the whole story. Because, of course, in the real world, we know that SUSY is not an exact symmetry. Because if it was, you would just find, for example, that the electron's partner would be sitting around for us to discover in colliders, or anywhere else. So, from all our experimental constraints, we know for a fact that SUSY can't be an exact symmetry of nature, and in fact, it must be broken at the very lowest scale, at the weak scale. Okay? So SUSY could be exact at the weak scale or above, but it better be broken below it. Otherwise, we would have found evidence for supersymmetry already, all around us. Now, that might worry you. I've made a big fuss about this cancellation of quadratic divergences. Now I've told you it doesn't work because SUSY's broken. But it's actually okay in this case. Because if SUSY's exact, so what I've said here is the following, that supersymmetry is very pretty, it's very nice and symmetric, but it has to be broken, and it could be broken at any scale. Could not be there at all. It could be only effective at the Planck scale, in which case I'm not sure you really know what you're talking about. It could be effective at the gut scale. It could be effective halfway down. Or it could be effective right at the weak scale. And if it's effective at the weak scale exactly, then what's interesting is that these quadratic corrections that I've been writing down only go so far. So in particular, this expansion I wrote down before, where this was the cutoff that appeared in my momentum integrals, gets replaced by where SUSY's broken. So what happens is, you start at zero energy, quadratic corrections kick in and start contributing things because there's no supersymmetry, they hit the supersymmetric scale, SUSY is exact, and there are no further quadratic corrections. But it's actually okay if SUSY's broken at the weak scale, because if SUSY's broken at the weak scale, then What you have here now are two roughly weak scale numbers, the thing that appears in my Lagrangian and the thing that appears from quantum corrections. I just need them to conspire to give another roughly weak scale number, the mass of the Higgs. So this is no longer a very deep fine tuning, this is just something that could quite naturally happen. And so if Susie's broken at the weak scale, or roughly at the weak scale, TV let's say, then Susie in fact solves the hierarchy problem, even though it's broken at scales below this. This is very nice. So this is the reason that people are interested in supersymmetry colliders. If you just were interested in supersymmetry because it's pretty, you'd have no reason to think it should be at the weak scale. But because of this tight connection with observed quantities in particle physics, people are interested in the weak scale. Now, is there an alternative? Well, could it be that the fundamental scale of physics is close to the weak scale? If there is, then the hierarchy problem, as I already mentioned, is why is the Planck mass so big? Things to bear in mind are that electroweak interactions are tested down to ridiculously small distances because we have colliders. Okay? Whereas gravity, this thing that I'm claiming is unnaturally large, it's the Planck mass is unnaturally large, is only tested down to about, I mean, I'm being loose here, you know, 1/10 of a millimeter or something like that, half a millimeter. So one thing we do know is that there are no quantum gravity effects up to the weak scale, because if there were, then you'd have spotted them in colliders. So you'd see energy loss to gravitons when you collide positrons with electrons, for example. So these are things you have to be careful of if you're going to start messing around with the strength of gravity. So how could it work that gravity couldn't be fundamental? The strength of gravity couldn't be fundamental? Well, the idea is to go to extra dimensions. Suppose you live in 3+1 dimensions that you know and love, and there are d extra ones that are just somewhere. So in order to make it work, these extra ones, where I've used a capital D for reasons of confusion, then will have to be compact. You have to bind up these extra dimensions in a small way, and then the standard model particles you confine to a 3-dimensional submanifold where we live. Okay? Whereas gravity you let live everywhere. Okay? So the motivations for doing things this way, which I'll expand on in a slide, are that string theory contains objects in it that are called d-branes that allow you to localize gauge fields, but like gravity propagate everywhere in a larger number of dimensions. And it comes from the fact essentially that open strings, which must end on branes, describe things like standard model particles, whereas gravitational fields come out of open strings, which don't need to end on any branes and can just propagate them everywhere. So there are various string theory constructions, like for example, WIMP theory, which comes really from heterotic M theory, where this kind of setup can arise. But I just want to think about it phenomenologically. So there are several ways to do this. Let's start with the easiest, large extra dimensions. Suppose you have a 3+1 dimensional space-time, and you add on a torus, a d-dimensional torus. So d extra dimensions, each of which is just a direction that you've wound up into a circle. So let's just write one of these extra dimensions here, because my drawing skills are limited enough. So we live in 3 dimensions. If you have a particle sitting out in the bulk, and you're asking what's its gravitational effects, then the easiest way to think about what the gravitational field looks like, what the gravitational force looks like, for me at least, is to think of Gauss's law. So flux spreads out from this particle. Now if you're on very large scale, on very small scales, if you just surround this particle with a little sphere, then the sphere is in all your number of dimensions. Flux spreads out in all those dimensions. But it's very easy to see that Gauss's law tells you that the gravitational acceleration goes like 1 over r to the 2 plus d. Not what we measure in our world, just to remind you. Okay. On the other hand, on large scales, if you try to surround this point mass with a very large sphere, the flux can only spread out so far in this extra dimension that it stops spreading in those directions. Then it only can expand in the infinite 3 dimensions that we have. And consequently, the force law turns around. You pick up a sort of volume term here from the extra dimensions, but the actual dependence on the scale only looks like 1 over r squared from then on. And that is what we see in our world. And so, if you have a setup like this, it's possible to reproduce all the things you know about gravity on large scales, and only have a change to gravity on small scales. And tomorrow, when I talk about extra-dimensional implementations, approaches to try to get cosmic acceleration, I'll be writing down a model of extra dimensions where the exact opposite is true. But for now, this is the case. So the trick, of course, is to make the size small enough that you don't probe this region so far. So if you have this setup, then all you do is you identify your 4-dimensional Newton constant with the higher dimensional Newton constant modulated by the volume of the extra dimensions, or if you like, more appropriately to what I've said so far, the Planck mass squared is related to whatever the fundamental scale of physics is in your problem, the fundamental Planck scale of your problem, times the volume of the extra dimensions. And now you're almost done, because remember our goal here was to make M Planck huge. You'd like to make M Planck a weak scale, so that gravity is really technically weak, but only a weak scale only becomes gravitational scale because of these extra dimensions. So if the electroweak, if the fundamental scale of all physics is a TeV, then if you make the volume of extra dimensions big enough, M Planck can be still 10 to the 18 GeV or so. So generally, you need R to be given by this expression in this simple model. And in d equals 1, you clearly can't do it because your extra dimensions are tending to be bigger than the solar system. But as soon as you get to more extra dimensions, you can start pushing it down to areas where it's completely consistent with everything we've observed. So if you do this, you're solving the hierarchy problem. Well, that's not really true. I've succeeded in bringing down the scale to the weak scale, but I've paid a price for it. All we've really done is rephrase the hierarchy problem. We've changed it from a problem of very disparate energy scales to one of very disparate length scales. After all, I need to make these extra dimensions huge in fundamental physics terms. Much, much bigger than the inverse of the natural mass scale of the problem, which is the weak scale. And so there's a hierarchy all on its own that you need to explain. It doesn't mean this is a useless model. It's an incredibly useful way to think about approaching the problem. But on its own, it doesn't solve the problem. On the other hand, there are ways around this. And in fact, the easiest way is to say, well, these extra dimensions don't have to be flat at all. In fact, if you don't wrap up your extra dimensions on a torus and just have a product space, but instead you wrap them up on what's called an orbifold, a little line element. And most importantly, in the extra dimension, the line element, so here's the 3 dimensions we live in, here's the little line element between them. Then the metric in here need not be flat. You can put in a little cosmological constant here, -1 it turns out. And then the metric in here turns out to have this interesting form. It's what's called a warped metric. The factor here, the way you measure distances in your 4-dimensional space, depends on where you are in the extra dimension. So as I move along in Y, the actual effective 4-dimensional metric is getting rescaled by where I am in the Y direction. This is called warping, because you're bending the amount by which you measure distances in the space as you move along in the extra dimension. And what you care about from this is the following, that if I redo the calculation I did on the last slide, which I won't bother to do here in detail, the relationship between the fundamental scale of physics, which I want to be the weak scale, and whatever the Planck mass is in 4 dimensions, is now an exponential one, not a linear one, not a polynomial one, I should say. And because it's exponential, then it's very easy to explain the hierarchy. Okay? Because all I have to do is tune 2 numbers together that appear in an exponent in such a way that I get a scale that is different by 10 to the 15. That involves a tuning of about 10 or 30. So while I won't write down the equations here, they're not particularly illuminating, having a warped extra dimension, putting some general relativity in the bulk, allows you to solve the hierarchy problem in a fairly natural way. Okay? Something akin to what Susie does, but for completely different reasons. So how much time I have left? Half? Great. Thanks. Okay, now, there are many, many implications of having these extra dimensions. It's an incredibly rich structure. We could go on for many lectures, but for this purpose today, I care about is one of them. Namely the following. The theories that I've described are theories that happen on finite spaces. The 3 dimensions we live in are infinite, but the dimensions we're in are finite. And so when you compute the effects of having fields on those spaces, it's really like doing quantum mechanics in an infinite potential well. Okay? And one thing you know from that is that if you have any regular field that you would have in your normal four-dimensional theory, you also pick up now a tower of states of increasing masses, just as you do in quantum mechanics. These are what we call a Kaluza-Klein particles. They have increasingly high masses. They're called Kaluza-Klein because Kaluza-Klein, of course, had the first models of using extra dimensions in general relativity as an attempt to get electromagnetism as a geometric force. In the flat case that I described, the case where you just have the extra dimensions flat and up in a very boring way, then the Kaluza-Klein masses go just the way you'd expect them to. They have scales that are of size the extra dimension, and n here, just an integer, but you just keep adding 1, 2, etc., etc. That's it. So it's a tower of states. In the Randall-Sundrum model, the thing I described that has warping, and in more complicated large extra dimension models. So parenthetically, I'll say here that even if I didn't warp up my extra dimension, I kept it just as I did. The extra dimension was flat. I could still have very interesting things that are not tori that I wrap up my extra dimensions on. If I do that, the spectrum becomes incredibly complicated as well. But in principle, it's the same idea. You get a tower of states. So just to give you an example, in the Randall-Sundrum model, you can see that there is a set of excitations that appear in this cross-section here as a function of mass. So at different masses, you get a set of particles, increasing masses that you could measure in a collider, for example. This is slightly different than the example I gave you of flat extra dimensions. This isn't warped. Principle's the same. Okay, so I've described why the weak scale emerges from cosmology and freeze-out, and I've described why the weak scale is important in particle physics, and why we need some mechanism to tackle the hierarchy problem, supersymmetry, extra dimensions. What does that have to do with dark matter, other than it's something to do with the weak scale? Well, taking a step back and not talking about supersymmetry or extra dimensions for a minute, but making a much more general statement, there is an incredibly broad connection between any model of beyond the standard model physics that addresses the hierarchy problem and dark matter. And the arguments I'll make, which I'll make more precise for models in a moment, is the following. Any model that you introduce will have new particles at the TeV scale, because you're modifying the weak scale. They must be related to the standard model particles through new symmetries, because otherwise how are they possibly going to help you with the hierarchy problem, which involves delicate cancellations of one kind or another. So, for example, in the case of SUSY, you have the superpartners. In the case of extra dimension, you have the Kaluza-Klein partners. In other approaches, there are extra gauge and scalar fields, etc. Now, typically, something I haven't mentioned yet, but I will in a moment, anytime you introduce new physics at the TeV scale, although it's very nice to tackle the hierarchy problem, I already told you that the Electroweak model is beautifully tested. Any new physics is going to try to screw that up. In fact, worse than that, it's going to help the proton decay, if you're not careful. So to avoid things like proton decay, and to avoid conflicts with precision Electroweak tests, typically you need a new symmetry. Something that distinguishes the new particles from the standard model particles and suppresses the contribution in virtual loops of the new particles. In supersymmetry, this gets called R parity, as I'll mention in a minute. In extra dimension, it's called KK parity. In little Higgs model, it's called T parity, etc., etc. People are not very imaginative with their names. But if you have a new symmetry like this that distinguishes new particles from old ones, one of the new particles will be the lightest one. And it'll be stable, because it's distinguished by a symmetry from the old particles. And so now you have a new stable particle at the weak scale. And often this particle will just be an ideal WIMP candidate, because it's a new stable particle at the weak scale. It will live for the age of the universe, and it will freeze out at the weak scale. I've deliberately made this argument very general. It should be clear to you, and I hope it will become clear on the next few slides, that computing whether it's an actual WIMP candidate as opposed to an actual WIMP as opposed to a candidate is where all the devil is. So let's move on to some examples. How about supersymmetry? So, as I mentioned, if you want the proton to remain stable in agreement with precision Electroweak tests, you have to introduce a new symmetry which is called R parity. It says that the parity of a particle is 1, the parity of an antiparticle is -1. So what are the consequences of this? Well, firstly, superpartners are produced in pairs, and they must decay to other superpartners. Okay? In order to, if you have a reaction that you write down an interaction, you have to preserve arc parity in the equation. So the lightest supersymmetric particle, usually called the LSP, is absolutely stable. Okay? And one thing that cosmology tells you immediately is that if you're going to have a stable particle that's produced out of some particle physics model, it better be charge and color neutral. Because cosmological bounds tell you that the universe absolutely does not have a large abundance of charged particles in it. In fact, it tells you an extremely small abundance, if any at all. In many of these models, the lightest superparticle is what's called the lightest neutralino. Well, I'll show you the next time. And because of the things I've said here, it's a weakly interacting massive particle and an actual dark matter candidate. So I'll just remind you before I show you more details about these things that we invoke this whole structure, supersymmetry, everything else, at the weak scale to address the hierarchy problem. This dark matter candidate, the LSP, often the neutralino, came for free, completely for free. What about extra dimensions? Well, here you need the same kind of symmetry. In many of the models, you just get this, because actually the Kaluza-Klein number, the number of Kaluza-Klein states can be conserved naturally due to conservation of momentum in these extra dimensions. So that's something that you get naturally, but of course it's easy to break that in a number of models. Okay? It turns out that all you really need to protect harmful corrections in extra dimension models is KK parity, just a similar thing to what I wrote down on the last slide, distinguishing the KK particles from the non-KK ones. Now, in this case, if you let's just restrict our attention to the first level KK modes, with the assumption that the higher ones are going to be just heavier and less important, then anytime you look at a collider or elsewhere in the universe, when you look at KK modes being produced, they have to be pair produced because this number has to be conserved. The lightest first level KK mode, which will be lighter than the higher KK modes clearly, is stable for the reasons that I mentioned here, and it's usually called the LKP, the lightest Kaluza-Klein particle, but not the LKKP. And any first level KK mode has to then decay to regular old zero modes, which are what I mean by standard model particles, and the LKP. So at the end of the day, you just end up with LKP from any process. And that's a natural dark matter candidate, for the reasons that I've mentioned. And once again, this whole structure was invoked to address the hierarchy problem, and along comes this particle of free. So just to give an example, this is a slightly more exotic model of extra dimensions, universal extra dimensions, where all particles propagate in the bulk. And you have this hierarchy of different excited states that arise due to excitations of the photon and the W and Z. These are all KK excitations of regular standard model particles. And what you find is there's the lightest one, in this case it's actually a photon. This is quite a KK photon, this is quite an exotic model. And it's this lightest one that would be the dark matter candidate in a model like this. So what's the dream? The dream is that you turn on your colliders, you find the Higgs and what breaks electroweak symmetry and all those things that particle physics is fascinated by. But most importantly, perhaps for this audience, you might be able to use them as dark matter laboratories. So you might discover WIMPs, if they're of the form that I just told you, and you can determine their properties, and then the hope is that the consistency between the particle physics properties, okay, their cross sections that you could measure exquisitely well at colliders, their masses, and then you could figure out from that precisely what the freeze arc should be. And then you go measure their abundance in cosmology, and the hope is that these things agree. And if that's the case, then what you'll get from this, as well as finding 25% of the universe, is you'll extend our understanding of the universe back from where it currently is in nucleosynthesis, which is our earliest direct test of the Big Bang, but minutes after the Big Bang, back to about 10 to the minus 8 seconds, okay, in a very similar way. And as I said, compare this to what was a spectacularly successful understanding of Big Bang nucleosynthesis, which came from understanding nuclear physics in the lab and putting them in an expanding universe and comparing with observations of cosmology. So it'd be the same program, much earlier times, much higher ranges, much bigger experiments, much bigger experiments. What are the challenges from a particle physics point of view? Well, everything I've written on so far, this is a 50-minute lecture at a school. I'm not going to do these things. But I've been writing down a cross-section and saying things are of order 1. You know, We measure things quite precisely in cosmology, and by we, I mean you. Okay. So, you know, the mass and cross-section expectations of a given particle physics model depend on very detailed understanding of the modes of annihilation to determine the freeze-up balance correctly. Is a particle candidate really a good dark matter? Is it really dark matter, or does it miss? Okay? Do they annihilate through S-wave processes or P-wave processes? If they annihilate through P-wave processes, by the way, you need a bigger annihilation cross-section than S-wave ones. It changes the dynamics. And this is a very model-dependent statement, as you might imagine. Okay? The spin of the dark matter particles is therefore crucial. You have to figure that out in a given model. And there are other more technical possibilities that can mess with your normal expectation of what the abundance can be. So for example, if you have a dark matter candidate in your model and another particle that is incredibly close in mass, it's possible not only, all the way down to freeze-out, it's possible for annihilation not only to happen directly, but via one of these particles that are very close in mass. That's called co-annihilation. It can completely change what you think the abundance is. So this really has to be carefully computed in every given model. And it's a real challenge. The big question for particle physicists, if you care about dark matter, is can the LHC and future colliders perhaps identify the candidates that people talk about in current models and distinguish these, what we call thermal relics, distinguish between the various possibilities, LKPs, LSPs, etc., etc. That's the big challenge. And of course, if you want to achieve this, if you want to be able to surmount this challenge, then you need detailed studies. And one problem, or let's call it a challenge in this field, is that in supersymmetry, I think this is kind of heresy, it's fair to say that not much is known. Now, that's not quite true. In various limited versions of symmetry, like M-Sugra, a lot is known. But in general, it's not even known generally what SUSY should give you. And in other models, there's only broadly typical bonds and values you can quote. This is not to take issue with the huge effort that goes into these work from many people across the world. It's just to say it's a very hard problem, and there's only so many people that are working very hard on it. So let's focus at least on some place where things are known. Let me start by giving you just some rough examples. Okay? In the universal extra dimension model, dark matter, you know, some calculations put it around 600 GeV. In brane-on dark matter, it says dark matter that comes from the oscillations of these branes I talked about. You people tend to know that the dark matter mass is greater than 100 GeV. Randall sun-driven can be quite low, which is nice. People have just started to probe these things, really, in the last 10 years. Well, let's finish up with an example that is more specific. So let me talk about the MSSM, the minimal supersymmetric standard model. The most minimal thing you could write down that extends the standard model, solves the hierarchy problem, and is supersymmetric. There's precisely one superpartner for every standard model particle, and there are no other particles that you care about, except there are two Higgs doublets, not one. Why two? For a technical reason. You need to cancel the triangle anomalies. I talked about anomalies last lecture. There were anomalies in global symmetries that are allowed. Anomalies in gauge symmetries, the theory is useless. And so in the MSSM, you need to introduce two Higgs doublets to stop living in an anomaly in a gauge symmetry. Supersymmetry is not precise, of low energies, you need to break supersymmetry. And you do that via the introduction of terms that break SUSY softly. Soft here is a very precise meaning. It means that you break SUSY enough, but you don't break it so much that that lovely cancellation of quadratic divergences is ruined. This model has 124 parameters. So Alessandro was saying, you could fit, what, an elephant with 15? You could fit the entire Amazon rainforest with 154. So what do people do? Well, they do what they can do. The typical thing that people have done is to constrain to various subsets of these things. And the one that's been very popular is what's called M-Sugra. If you take supersymmetry and you try to turn it into a theory that incorporates gravity, or rather I should say, if you take supersymmetry and turn it into a gauge symmetry, into a local symmetry, you're forced to incorporate gravity, and those models are called supergravity models. And then, if you run the parameters of those models up to the grand unified scale, there's sort of a nice suggestion of a particularly pretty subclass of these models that you would like, and they're called the minimal supergravity models. These 224 parameters really come down to these on top of the normal standard model ones now. And I'll say what these are. M0 here is the mass of all the new scalars you have evaluated at the gut scale. M half is the mass of all the gauginos, the partners of the gauge particles, up at the gut scale. A0 is one of these soft SUSY breaking terms evaluated up at the gut scale. And tan beta is something you'll find everywhere when you talk about the null supersymmetric standard model. It's the ratio of the vacuum expectation values of the two Higgs particles. Mu here is the supersymmetric Higgs mass term. And the magnitude is fixed, but I really care by evaluating things at the gut scale. So here all I really care about is its sign. Okay? So this is a very manageable number of parameters, and in fact it's 5, and so it really is a standard model in the sense that we've been using it here in this conference. So in MSUGRA, a number of years ago, Jonathan Feng and I chaired a committee that was supposed to sort of come up with a set of, a piece of work to understand the connections between particle physics and between cosmology and the linear collider, when people were still fantasizing about a linear collider. And as part of that work and part of a broader effort, a bunch of benchmark examples were written down by people like Michael and Michael Paskin and people like that. And so I'm just is one slice through the parameter space that I'm showing you here, that M1/2 parameter and the M0 parameter. And all I really want to point out is that when you look in this whole parameter space, it turns out there are very cleanly defined regions where you can get the right dark matter abundance, and everywhere else you cannot. So in this model, for example, if the parameters are in this region, you get a charged LSP, and I told you that's a big no-no. If you're up here, the electroweak symmetry doesn't break at all, and that's not good since we like electroweak symmetry breaking. There are other constraints you get, and the upshot is that there are only some very narrow regions where you get the right relic abundance. Now you might say, well, that's very disappointing, or you might say, well, that's what you'd expect, because you want to come up with a very precise relic abundance. So these get names. They're called the bulk region, the focus point region, the co-annihilation region, which is where this crucial annihilation with other similar mass particles is important, and the rapid annihilation funnel for technical reasons. But all I really want to point out is that you can choose representative points in these regions and ask, how well could our experiments do in nailing down the identity of this dark matter? So I'm going to finish, essentially, with a very, very optimistic example, since it's good to be optimistic. So I'll follow, essentially, what I said about now. So this is an MSUGRA example. It's what's called the bulk region example, LCC1. It's got a positive mu. These are the values of the parameters that I told you you would need. That's it. So what happens? Here's what happens. This is a plot of the mass of the dark matter particle against the abundance. The yellow region, roughly, is the bombs that come from WMAP. Okay? So that's nothing to do with colliders. This is just telling you, whatever the mass of your particle is, if you want it to be dark matter, it better lie in that yellow region. The blue region is how well the LHC should be able to constrain the mass if this is the real model of nature. And it's actually quite a narrow range if you look on it. Okay? Planck, which we've heard first results from in this conference, should come along and should significantly narrow these bars and tell us that nail down the abundance even better. And just for fun, if you were lucky enough to have a future international linear collider, about $20 billion sitting around, you don't know what to do with it. George was excellent. So then you could nail down. If this were the real model of nature, and it would solve the hierarchy problem, it would do all the nice things for you, LC would nail you down in here. Now, if this happened, this would be a quite remarkable thing, I think you'd agree. You would know what the dark matter was in the case by this, and you would know it very, very precisely indeed. So this is a very optimistic example of what this interplay between colliders in this case and cosmology can give you. Now, I'll finish by just pointing out, in a woefully unfair way, because of time constraints and because I wanted to focus on something rather than talk about everything, there are many other options, of course. Okay? Dark matter doesn't have to be WIMPs. But what I like about WIMPs is that they're very testable and they tie in incredibly well with physics at the weak scale. Okay? There are many other well-motivated particle physics candidates. So things that fall into this category that I mentioned, that particle physics has a problem, you solve it with particle physics and it spits out a dark matter problem. And the best known one is the axion, which is invoked to solve the strong CP problem of particle physics. And I don't have time to talk about it here, and there are many constraints on these models, and there's a very nice paper back there by Graf and Steffen And I encourage you to take a look, a nice poster, I should say. And I encourage you to take a look. This actually concerns the thermal analysis of these things. And there are many other ways to detect dark matter. Okay? You can do direct detection. Okay? You can build a giant detector, make it as quiet as you possibly can, either by cryogenically cooling it and sticking it under a giant amount of the Earth so that it's shielded from cosmic rays, or by looking for angular variations in it as the Earth moves around. But in any case, you can use those objects by just waiting for dark matter particles to come in, and once in a while then they'll smash into your detector and give you a signal. You can put bounds on the cross-section and the mass. And these are current bounds from, reasonably current bounds from a host of experiments all around the globe, which I haven't had time to talk about. Okay. There's also indirect detection. You can look in the galaxy and look at places you expect densities to be high, like the core. This all depends on astrophysics and how cuspy are the centers of galaxies. You can look for dark matter to annihilate and give off signals, and people do that. In fact, there's been a bit of fuss over things like that in the last few years, although it seems to have calmed down a little bit recently. And I'll just point out that for some models, even some supersymmetric models, there are some very strange ways to use colliders to find dark matter indeed. So one thing I'll just mention in passing is that in some of these models, it's possible for the dark matter to be something that you would not measure in a collider, like a gravitino, but for freeze-out to be governed by something that's very close to it in mass, like a regular old neutrino. And then what can happen in these models is that you produce a particle in the collider, it leaves the collider, you never measure it. But if you build a giant tank of water outside, you can slow it down and just collect them. Then after about a month or so, or weeks, it'll decay away and you can detect the energy and see if those particles are there. So I don't say this because I want to go into it in detail, but just to point out that phenomenology, the particle physics phenomenology, can be very, very rich, even within series models. And things could be much more complex. Dark matter could have interactions that are more exotic. It can interact with dark energy. It can interact in very interesting ways. It can have its own set of interactions beyond the ones I described in the standard model. And they can have interesting consequences all of their own. And I couldn't help advertising that Jonathan Fung and I had an article in November Scientific American where we talk about that in some detail. So read that if you want a quick summary. Let me make some final comments. The nature of dark matter is another of these central issues that particle cosmology has to face. It's an important part of the puzzle of the energy budget of the universe, and there are many possibilities, but I do find the WIMP possibility and their intriguing connection to this TeV scale physics and hierarchy problem to be quite compelling. Axions and other things are important, and they're also there for good particle physics reasons. So it's certainly the comprehensive list that I've covered here. And for WIMPs in particular, there could be important evidence in upcoming, in the next few years' data from the LHC. And that might provide us with impetus to even build future colliders if we were really determined to figure out how the universe works. Thanks.
Are there any questions?
I have a combination comment and question. And so you picked what is the standard lore about CZ and supersymmetric particle and everything. And it's a very beautiful, compelling story. And it prejudices, so this ties to my earlier comment about the largest systematic error in cosmology is theory now, which is a great advance.
Yeah, absolutely.
Right? And so, like when Martin White was talking about how very active calculations, it's all 1% level. I mean, it's all, the theories are right to 1% level. That's sort of issue.
Right.
And here, you're showing, because of the beauty and the motivation of it, you're showing strong theoretical prejudice. If you actually look at the data, the dark matter could be anything from the KeV scale up to the TeV or perhaps larger scale. Yep. And in fact, the data probably are fit slightly better by 10 keV, WIMP-ish kind of particles. There you're having, your prejudice is to put in exactly the neutral, the neutral particle with exactly the weak scale, whereas sterile neutrinos would have a coupling that's much lower, produced by other mechanisms. Gravitinos can be produced by other mechanisms.
Absolutely.
And they could easily be anywhere between the few keV and the GeV kind of scales. And they're not going to show up, right? there's quite a reasonable phase space for the LHC results being essentially upper limits, and the dark matter detections being upper limits, and so forth. So, in the question about distinguishing, the kind that Ed Bertrand was talking about, what's the most important, what was the number one problem? I would have said, observationally, it would have been to measure the scale factor of the universe versus time. So you have kinematics, and then you have physics, the dynamics and predictions after that. Is general to be right? Is this particular model right? So again, my argument here is you have a strong theoretical motivation. Don't let the students get too prejudiced by that, because there should be an observational one which says we still have this huge range open. And the question is, do you have any favorite models, that fall in between? Right? They wouldn't show up. It's good to be optimistic that we're going to solve the problem in a short time, but do you have some models that will show up much later?
I don't have favorite models in this game. I think everything you said, I think, is right. That you wouldn't want observers to be told that there's a beautiful connection between weak physics and dark matter, and then run away and focus all their efforts on that connection between weak physics and dark matter based on what it's like.
That's how the experiments get funded.
Well, I don't think that's true. I mean, if you...
No, it is true.
If you look
strong bias towards the theoretically motivated thing.
No, but if you wanted to, no, I'm not sure I agree with this. I mean, obviously there's some bias, but if you want to build a direct detection experiment for dark matter, you're just going to build something big that's sensitive, right? I mean, what else can you do? No matter what the dark matter is, it's going to come. Your only option really is for it to come in and smack into things, and you to measure what comes out of that. Now, it is true that the examples I showed, for example, in the direct detection, cover some region of the particle space that I mentioned in this talk. It also covers a whole bunch that's not in these mountains. So I think there, you're just covering, I think there is an example where you're doing exactly the right thing. You're building the best experiments you can, and it would be great. I mean, people certainly give talks where they say, what portion of the SUSY parameter space we're ruling out. And you shouldn't care too much about that. But they're just building the best experiments they can, I think. So I think that's the right way to do it. I would basically agree with you. I don't have favorite models that lie elsewhere. There are, as in the case of baryonysis, there are many, many things that dark matter could be. And you have to, it's a sort of a message to the students that you have to choose what you want to work on. If you care about the connection between particle physics and cosmology, my own taste is to spend more time on those models that have a connection to other observational tests. And in this case, you have a clear observational tests in the LHC, etc. But as you say, it doesn't have to be there. So certainly there's a large phase space, even in the SUSY models, where you won't find them in the LHC and you won't find them in direct detection methods in the next generation. But you might. And even the SUSY models go down, as you say, they're very variable masses. So I don't have much to add to what you say. I would agree with this.
So the cancellation of quadratic versions is a strong motivation for MSSM, but even within the MSSM framework, there are some problems like the new problem and the smallness of the CP violating phase. So would you comment on that, and rather would you say that there is a good model which is very consistent in the sense that
Right, so the question, if you didn't catch it, is that it is true that, say, the MSSM does a nice job of canceling these quadratic divergences and solves this hierarchy problem that I mentioned. But it is true also that it comes with its own set of theoretical issues, such as the mu problem. So I mentioned this parameter mu. The question of what sets its value is a very tricky one in the MSSM. It's also true, which I didn't emphasize here, but maybe it's worth saying right now, that already current experimental measurements make it that you do need some fine-tuning, even to make the MSSM work, which is the hierarchy problem. So your question was, are there good models that tackle these things? And of course, like any good particle physicist, I'm going to tell you that people are very smart, and they have found ways to tackle this. So the mu problem, of course, gets tackled with things like the next to minimal supersymmetric standard model, okay, where you have extra particles beyond the minimal ones that you produced. You make, for example, the mu parameter into the vet of a field, in the case of dynamics, etc., etc. So certainly there are models that do this, Whether there's one of those that we'll end up being completely happy with and has none of its own issues, that's beyond me to say. I don't know. It sort of depends a lot on what comes out of colliders. And I should also say, sort of partly in relevance to this and partly back to what George said slightly, that one thing to say about the LHC is that it's a hadron machine. And the thing about it being a hadron machine is that not only is it hard to, as you say, there are regions of parameter space where we're not going to, we're just not going to probe. It's also true that there could be regions of parameter space relevant to some of these models that you're talking about that are more exotic, that we will probe, and we'll never know that we probed. Because built into the LHC, and it's certainly relevant to what George said, are some theoretical biases. With the lepton machine, you just keep all your data, and later on you go look at it. With the hadron machine, you're spewing off so much, well, I want to say junk, but I guess that's it. Someone said earlier that all data is all noise is data, but you're spewing off all this data. That's something, and you've got to choose which of it you keep. And so it's possible that some of these exotic modifications you won't find precisely because you're not looking for them. You do the best you can, but it's a point.
In the direct detection experiment, usually there is this DAMA experiment. Can you comment on DAMA? Because it seems that they found something.
So the DAMA experiment is an annual modulation experiment. So they do not, experiments like the ones that I showed you on that plot, their goal is sit there, try to get rid of all backgrounds, best you can, and wait for dark matter to come in. The goal of something like DARMA is don't worry too much about the backgrounds. Actually, that's an unfair thing to say. Try to understand them, but don't try to shield yourself from them. And then wait as the Earth goes around the sun. If you do that, the solar system is going around the galaxy. Part of the time you're going into the incoming wind of WIMPs. Part of the time you're going away from the incoming wind of WIMPs. And there should therefore be an annual modulation of the signal you see. DARMA claims to have seen such a signal, and I think it is unambiguously true that they have seen such a signal. The question is, have they seen a signal that is dark matter? So, the simplest dark matter candidates, in fact, more than the simplest, many dark matter candidates of the types that I described, if they were to be the candidate that DARMA saw in its annual modulation, would have appeared in the other experiments that I showed you, and it has not appeared there. So there's a conflict between that data, and I'm certainly not an experimentalist, and I won't pretend to be one and tell you why I think that is. It's also true, though, to be fair, that there are other more exotic examples of what could be a candidate that would have sufficiently interesting interactions that they would not appear in some of those experiments, but would appear in the DARMA experiment, and therefore would be a consistent explanation to all the data. They're quite exotic, and new experiments are coming along all the time, which are decreasing the possibility of that being the case. So, you know, if I think you asked the question, you're probably aware this is something of a controversial topic in the dark matter community. It's not very fruitful to get into controversy. DARMA has seen an annual modulation. We'd like to know, is it really dark matter? Is it really something else? Is it some systematic? Is it something to do with an error in the experiment? I have nothing to say about that, but it's something to be understood. But there certainly are dark matter models. You chose to take that route, which currently could explain both those bits of data. That's interesting in its own right.
I think it's time to have the coffee break, and we have to return now. Thank you.